Alright guys, so here's the video explanation of the 3 voting methods that you're going to be tested on Monday: Hamilton, Jefferson, and Webster. So my first example is a Hamilton method with standard quota, lower quota, upper quota, initial apportionment, and final apportionment. So we're going to take a look at the answers. Okay, this is what the original problem will look like, and this is what the answers are. Alright, the first thing we're going to do is get our total population by adding all the populations. We get 19,317. We divide that by the reps, and that's how I get this standard divisor. So 19,317 divided by 35 is 551.91. I take this standard divisor and I divide it to each population. So 2,413 divided by 551.91. 3,924 divided by 551.91. I do that for each of the 6 populations, and I get standard quotas. We want to get our standard quota, we want to round to the nearest hundredth. So when I do those 6 division problems here are my 6 standard quotas. My lower quota is literally the number before the decimal point. I add it up, I get a total of 33. My upper quota is the number after the decimal point. If I added this up, even though I don't necessarily have to, I should get 39. I should get 6 more because I have 6 groups here. 5 and 8 is 13, 13 and 6 is 19, 19 and 4 is 23, 23 and 7 is 30, and 30 and 9 is 39. So I must have done it right. My initial apportionment, I literally copy down my lower quota, and what I need to recognize is my lower quota is 2 less than the amount of representatives. So I need to give away 2 more representatives. I give them to the populations that have a standard quota whose number after the decimal point is highest. In this case, 0.74 and 37 are the 2 highest numbers after the decimal point, so they get the 2 additional votes. I add them in the initial apportionment, and my final apportionment should equal 35. 5, and then we keep 7, 5, 3, 6, and then add 1 to the 8 and get 9. And that's how you do Hamilton method. Very straightforward. Jefferson method, a little bit more complicated. So I add up, I get my total population of 25,983. I divide by 45, and I get a standard divisor of 577.4. Then I divide each population by the standard divisor. So for example, 5,478 divided by 577.4 gives me 9.49. We're always rounding to the nearest hundredth. And then I take my lower quota, 9, 6, 8, 4, 5, 10. Add it up and I get 42, which means I have 3 more reps to give away. Now, how do I give those 3 reps away? They go to whatever reps I can get to get a new lower quota that equals 45. So essentially my lower quota right now is 42. I need to get a lower quota that equals 45. And I do that by reducing the standard divisor. Now, I essentially need to get 3 standard quotas to move up 1. This is an obvious one, the 10.99. It's the biggest population and it's closest to the next number. Then I have a choice. It's really between groups A, B, and E will get the next 2 spots. E and B have numbers that are closer to the next number, but A is the biggest population and A would move the quickest. So I need to guess and check at numbers that are lower than 577.4 to get a modified standard divisor. My best guess is I think E would get the last vote or last extra rep. So if I take E, 3,256, and I divide it by 6, which is what I want my modified standard divisor to be, or my new standard divisor, that'll give me a modified standard divisor to work with. Really, any number between these 2 will work. If I divide each of my populations by this new standard quota, I get 10.1111 or 10.11, 6.98, 8.66, 4.49, 6.01, 11.71. And you can look at my new lower quota. This goes from 9.49 to 10.11. So this lower quota is now 10. 6.98 and 6.55 have the same lower quota of 6. 8.13 and 8.66 have the same lower quota of 8. 4.21 and 4.49 have the same lower quota of 4. 5.64 goes to 6.01. The new lower quota is 6. 10.99 goes to 11.71. The new lower quota is 11. And this final column adds up to 45. So essentially, I have to guess and check at a standard divisor. So when I divide it through by all 6 populations, my new lower quota is 45. Remember, even if you don't pick the right one on the first one, it will get you closer to the correct answer. Now for Webster method, we have 2 options. The Webster method, we round normally. So we still get our total population, 42,667, divide by the reps, 52, and get a standard divisor of 820.52. When I get my standard quotas, I get 10.40, 9.35, 5.80, 7.30, 11.12, and 8.02. I get those numbers by dividing each population by 820.52. And I round normally. 10.40 is 10, 9.35 is 9, 5.80 is 6. It's no longer a lower quota. 7.3 is 7, 11.12 is 11, and 8.02 is 8. And I have an initial apportionment of 51. So I have one more rep to give away. It's an obvious one. I need to get 10.40 to at least 10.5. When I divide by any number between these two, and I divide all 6, I get 10.51, 9.49, 5.87, 7.39, 11.26, and 8.12. When I re-round normally, the 10.51 goes to 11. Was at 10, it goes to 11. The rest of them rounding normally stay at the same number. 9.49, 5.87, 7.39, 11.26, and 8.12, all round as they did previously. Now the one unique thing about Webster method is sometimes you'll end up with too many reps. So if that's the case, you need to now raise your standard divisor. Remember, in Jefferson method, or when the Webster method gives you too few votes, you literally had to reduce the standard divisor. Now we're going to raise it. Okay. And in this one, when I round normally, I get 11, 10, 6, 7, 11, 8, and I get 53. I need to get to 52. 9.5 is the obvious one to move, because if I can get this down to at least 9.49, I'm going to be able to get my correct number of representation. Notice I do not raise this much. It got raised a little more than 1 to 821.682, and any number between 821.82 and 823.16 should work. So when I do this, now I divide all my populations by a number in this range, and I'm going to get 10.5, which still rounds to 11, but 9.48 now rounds down to 9, so I lose that one rep, which is what I was looking to do. 5.66 still rounds to 6, 7.2 still rounds to 7, 11.26 still to 11, and 8.12 still to 8. And that's how I get my final answer.